David Randall is an expert in all things atmospheric and how they influence the climate. I guess would say he's a particular expert in how clouds affect the climate. Most recently, his research has been involved in trying to develop parameterizations for the representation of clouds and convection in climate models. He's the editor of General Circulation Model Development, published in 2000. His primer, Atmospheric Clouds and Climates, was published earlier this year, and he tells me that he's working on a bigger book on the general circulation of the atmosphere and its role in climate. So, Professor Dave Randall from Colorado State.
Thank you. All right, so the starting point for this discussion is going to be about radiation flowing through the atmosphere. I'll come to other subjects in a little bit. But the simplest point to make right at the beginning is that the Earth is very close to energy balance. This can be stated based on measurements now from satellites. The difference of the Earth's net energy flow at the top from zero is right at the limit of what can be measured today, something like half a watt per square meter. So the sunshine that comes in is absorbed by the Earth, which, as you'll see in a minute, is mostly absorbed at the surface by the oceans and the land, is balanced by infrared radiation going back out to space. That's how the planet balances its energy budget. And the picture on the right there shows the sun. It's actually somewhat further away than the picture would indicate. And the picture on the right side is a Earth radiation budget satellite. So I'm going to put a little equation at the bottom here to warm you up. I'll come back to this later in the talk. But the left side of the equation is the absorption of solar radiation. S is the energy output of the sun. Alpha is the Earth's albedo, which is about 0.3. Pi is pi, and A is the radius of the Earth. On the right side, we have the infrared radiation that the Earth emits. So the starting point for that is sigma T to the fourth. That's the emission by a black body at temperature T. And this gets multiplied by the area of the sphere, 4 pi a squared. And then finally, there's a factor epsilon that measures how easy it is for an infrared photon to travel through the atmosphere from the surface to space. So if epsilon is 1, that happens very easily. If epsilon is 0, it doesn't happen at all. So we'll come back to that. At any rate, energy balance is the starting point. And so I have to say just a little bit about the degree to which the atmosphere is transparent to radiation. So there's a lot of detail on this slide, and we can't talk about all of it, but what we've got here is along the horizontal axis, different colors of radiation. The solar part of the spectrum is on the left side of the diagram. Visible radiation right there in green. A little bit less than a micron in wavelength, down to something like 0.3, 0.4. Ultraviolet is shorter wavelengths than that. So some of this is coming from the sun. And then near-infrared radiation also comes from the sun. This is a bit too red for us to see, but it is coming from the sun, so we distinguished it from this part, which is the radiation emitted by the Earth. This is the part that goes back out to space. And what you see above here are essentially the absorption bands due to various gases. So here's water vapor, carbon dioxide, and so on. And gray means lots of absorption. So the top row here is the total due to all these various species below. And so what you can see, for example, let me see if this works, is that ultraviolet is being blocked, good for us, by ozone. And infrared, thermal infrared emitted by the Earth is being blocked mostly by water vapor and carbon dioxide. Methane also does a little bit of that. And the gray here measures the extent to which these various colors of radiation can travel through the atmosphere, either from the top to the bottom or from the bottom to the top. And the gases that block the outgoing infrared are the greenhouse gases. And they're tiny fractions of the composition of the atmosphere. Okay, so a little bit more detail on this. And again, too many numbers to talk about, but there's some things here that are actually quite important. So this is the sunshine coming in from space, and there's part reflected from the atmosphere and part reflected from the surface and so on. Absorbed by the surface, 161 watts per square meter, joules per square meter per second. And then over here, we have the infrared going back out. So here we have 396, a big number, coming off the surface, trying to get back out to space, but it's partly blocked. Meanwhile, the atmosphere itself is emitting to space, and the number that makes it out the top is 239, a lot less than this. So these photons that would love to get back out to space are not able to do so very efficiently. This ratio is about 0.6. But very important point, the atmosphere is emitting down as well as up. You know, the emissions in all directions. Some of the photons go back down. 333 watts per square meter down. Compare that to this number. It's twice as big. There's twice as much energy coming down from the atmosphere as there is absorbed from the sun. Finally, we have these things in the middle of the diagram which have to do with clouds and water, and I'll talk about that here in a second. So solar radiation absorbed by the surface, 161. Infrared absorbed by the surface, 333. Just to make the point again, this is twice as big as that. So this really keeps the planet much warmer than it would be if we didn't have an atmosphere. Meanwhile, of course, the surface is also emitting upward, and the net radiative heating of the surface, including everything, is about just under 100 watts per square meter. 100 watt light bulb per square meter. So how do we balance that? The surface has to balance that radiative energy input, and it does so mostly by evaporating water. So it cools the surface in the same way that this little guy's being cooled as he got out of the swimming pool, and he's all wet and he's feeling chilly. This is actually a pretty efficient process because it takes a whole lot of energy to evaporate 1 kilogram of water. 2.5 million joules of energy to evaporate 1 kilogram of water. So let's ask, if 1 kilogram of water had 2.5 million joules of kinetic energy, like you shot it out of a cannon, how fast would it be going? You can do the arithmetic probably while I'm speaking. Mach 7. That's a lot of energy. The atmosphere is cooled by radiation. Surface is warm, the atmosphere is cooled. This is infrared radiation actually in the 6.7 micron band, which is chosen because you can see the water vapor. That's what these swirls are. 6.7 microns is efficiently absorbed and emitted by water vapor. So this is an infrared negative. The white means cold and the dark means hot. And you're seeing water vapor features here, but you're also seeing the effects of clouds. And the clouds you see are the cold ones, the high cold ones. So the top of this hurricane, for example. Okay, so we said that the radiative energy input to the surface is balanced by evaporation. What balances the radiative cooling of the atmosphere? It's mostly condensation. It's the opposite thing. So condensation of water vapor, again, 2.5 million joules per kilogram. I related the evaporative cooling to a guy climbing out of a swimming pool. You can do the same thing with the warming. Think about a sauna. When you go into a sauna and you pour water on the hot stones, it changes to vapor, and you feel hot. Why do you feel hot? Because the vapor is condensing on your skin. And the heat is being released, and that is actually the reason you feel the warmth. So let's talk now about clouds. Here's a little recipe for making a cloud. Rising air expands and cools. So clouds mostly form in rising air. There are exceptions to this, but that's mostly true. Cooling leads to condensation, just like a cold windshield has dew forming on it in the morning. The heat release, 2.5 million joules per kilogram, warms the air as the vapor condenses, changes into liquid. And the warm air continues to rise because you've warmed it now. You've added heat to it. And so it cools some more by expanding some more, and you get more condensation. So it's a positive feedback. It's an instability, actually. And it gives rise to these beautiful clouds that we call cumulus clouds. And the next time you see a cumulus cloud, just remember that's where it came from. It's something like this. The condensation in the clouds supplies buoyancy by heating in the same way that a burner in a balloon supplies buoyancy by heating. Okay, the top of my slide is not visible, but basically it says that the infrared radiation is leaking out to space, that is. You can measure how much is coming out. And you can ask, how warm would a black body be if it was emitting at that rate? And the answer is about 255 Kelvin, which is way below freezing. So then we can look at a standard atmosphere, and this solid curve is temperature in a standard atmosphere here. And you can ask, well, how high would you have to go to get to 255 K? And it turns out it's about 5 kilometers above the ground. So, roughly speaking, you can imagine that the Earth is emitting infrared out to space and getting rid of this energy by emitting it in the middle troposphere somewhere, 5 kilometers above the surface. But we have to get the energy up from the surface to that level somehow. So how does the energy get up there? Well, there are several parts to the answer, but one important way is clouds. The clouds that are growing upward under buoyancy that comes from the condensation of water vapor, they carry energy with them, and this is a really powerful effect. It's quite important. And thunderstorms are particularly dramatic and efficient ways of doing this, but even smaller clouds can do it too. So let's look at a plot here of the net radiation, the net energy in and out at the top of the atmosphere, so to speak, as a function of latitude. So here's the South Pole, the equator, the North Pole, and these are watt per square meter units here, and 0 means no net energy in or out, it's in balance. So in the tropics, we've got a net addition of energy from the sun, obviously. The sun is most effectively heating the tropics. And in the high latitudes here and down here, you've got a net loss of energy. Let me just explain. The solid curve is the annual mean, and the other two are seasonal curves. So somehow we've got to get the energy from the tropics toward the poles. And you can calculate the rate at which that happens just by integrating this curve. I won't show the details. But you get this curve, which is an amazingly smooth and simple curve considering that it's based on actual observations. This is averaged around all longitudes at a given latitude. So north of the equator, the energy is flowing toward the North Pole. South of the equator, it's flowing toward the South Pole. It's almost symmetrical, not quite. And the units are petawatts, 10 to the 15th watts. So how does that work? Well, part of it has to do with clouds again, but we have to talk about the large-scale circulation, and I want to start with the tropics. So here's a beautiful picture of Africa, which just came out a couple of months back, and you can see a lot of cloud here, and clouds, as I mentioned earlier, tend to form where the air is going up. So for purposes of this discussion, I want you to think that this white stuff here is basically indicative of rising motion, large-scale rising motion in the atmosphere, just north of the equator in Africa. This happens to be July. And then, of course, you see the Sahara Desert up here. And there's no clouds to speak of in that region. So what's happening is we've got rising air, don't know if you can read that, rising air here where the clouds are, and sinking air here where the desert is. And of course you know that if the air is coming up here and it's going down there, there has to be some kind of horizontal connection between the two, right? So that looks like this. This is a picture of something called the Hadley cell. It's named after a famous meteorologist of long ago. And these are just streamlines. So basically when they're going up and down like that, it means the air is going up and down. In this case, it's going up, and then it travels toward the north and sinks again somewhere in the in the subtropics around where the Sahara is, about 30 degrees north. So this big cellular circulation is carrying energy with it. And in particular, there's lots of thunderstorms here, and energy is being carried upward. The somewhat cooler air is sinking, so the net energy flow is up. It's also carrying energy poleward. The high energy air aloft and lower energy air near the surface. There's a net flow toward the North Pole in January, and it would be in the opposite direction in July. Mid-latitude storms also carry energy upward and poleward. So the idea is in the tropics, it's the Hadley circulation and the thunderstorms. And in mid-latitudes, it's these guys that we all experience here in North America, and again, thunderstorms. So a combination of ways. As we ride along this cloud sheet here, the air parcels are actually gradually rising. That's why you see a cloud. So the energy is being carried upward, but it's also being carried toward the north. So let's talk now a little bit about climate change. Let me check my time. What happens if we poke the system with a stick? The word stick is covered up here. Poke it with a stick. The climate system, as I've just explained, does what it takes to balance the Earth's energy budget. That's kind of the job of the climate system. And it does that by making cumulus clouds and the Hadley circulation and mid-latitude storms. What happens if we perturb the system? For example, by adding CO2. So we're going to go now through climate change on the back of an envelope. And part of the point here is to show you that you don't need a big computer model to understand the basic idea. And there are some equations with numbers on the next two slides, so I apologize in advance. I showed you this one before. So just to remind you, this is the solar radiation absorbed, and this is the infrared going out. There's the surface temperature to the fourth power. And this thing epsilon, again, measures how transparent the atmosphere is in the infrared. If epsilon's 1, it means the atmosphere is very transparent. Epsilon would be 1 for the moon. It doesn't have an atmosphere. And if epsilon was 0, there wouldn't be any emission. Okay? So for the Earth, epsilon is something like 0.6. Okay, so we're going to perturb this. And we're going to do it in a really simple and imaginary, idealized way. We're going to imagine that the only thing that happens is we increase CO2. And there are no feedbacks. So now the word feedback is used for the first time. So there won't be any changes in the sun. And there won't be any changes in the albedo either, because that would be a feedback. So the change on this side is going to be 0. Over here, we'll allow a change in the temperature, of course. And we'll allow a change in the infrared transparency of the atmosphere, because that's what increasing CO2 affects. Increasing CO2 will make this number smaller, makes the atmosphere more opaque in the infrared. So I just canceled out the pi a squares, and then I differentiated. So taking into account the sun doesn't change and the albedo doesn't change. And on this side, I get a delta, that's an increment, to the emissivity. That's going to be the CO2. And I get a delta to the temperature. Now, I want to assume that delta for the emissivity comes only from increasing CO2. No water vapor feedback, which I'm going to come to in a minute. No changes in cloudiness. Only CO2. So if you just shuffle this around a little bit, cancel out the factor of t cubed and so on, you get this little equation, which says the change in the surface temperature is that. So now I'm going to the next slide. We're going to put some numbers in, and this same equation is going to appear at the top. There it is. So the actual emission from the Earth now is about 240 watts per square meter. That's got the factor of epsilon in it. We know from essentially spectroscopy that if you were to double CO2 and not allow anything else to change instantaneously, that would cause the infrared going out to go down by about 4 watts per square meter. It's a -4, it went down. So we can divide these two things, take the ratio, and you get delta epsilon over epsilon, which appears right there, is -4 over 240. Okay, halfway there. Next thing we put in is the Earth's surface temperature right now is about 288 Kelvin. Remember that number, 288 Kelvin. So plug in the numbers, 1.2 Kelvin. Now, if you write small, you can fit this slide and the one before on the back of a business card, okay? This is not complicated. One of the most important points to make is that the change in the emissivity that I put in, the perturbation of the radiation budget, is about 2%. 4 watts per square meter out of 240. The change in the temperature is about 0.5%, 1.2 out of 288. There's nothing crazy about that. 2% change in the radiation budget, 0.5% change in the temperature. It'd be surprising if you changed the radiation budget by 2% and you didn't get something. Okay. Last subject, feedbacks. I just showed you that without feedbacks, the surface would warm by about 1.2 Kelvin for a doubling of CO2. With feedbacks, it doubles by a bit more than twice that much. There's a whole long list of feedbacks like melting ice and snow and so on. But the single most important one, arguably, is the water vapor feedback, and that's the only one I'm going to talk about here. So this little diagram explains what the water vapor feedback is. Let's say that we increase greenhouse gases, and that does lead to a warming. Well, the warmer air contains more water vapor, and water vapor is a greenhouse gas. It blocks infrared. So we get more warming, and it's a positive feedback. That's what the plus sign means. We also get an increase in the rates of precipitation and evaporation. The hydrologic cycle speeds up. And this is a very strong positive feedback. So why do we talk about water vapor, or sorry, why do we talk mostly about CO2 and not about water vapor? It's a fact that the atmosphere contains about 4 times as much water vapor as CO2 by mass. And both water vapor and CO2 are strong greenhouse gases. So why are we talking about CO2? Well, mostly 2 reasons. One is that human activity can double or quadruple or worse the CO2 concentration of the air, but we can't double or quadruple the water vapor concentration of the air. That's not possible. The temperature won't allow it. The second point is that unlike CO2, water vapor is condensable. It can change phase. We talked about this already. And that brings me to this last 2 slides. So here's the feedback again. We're going to play the movie backward, and what I mean by that is, instead of increasing CO2, we're going to get rid of CO2. We're going to get rid of all of the CO2, just arbitrarily, and ask what would happen. An interesting exercise published by Andy Lasis and colleagues about a year or 2 back. So we still have this positive feedback, but I changed the words: decreasing greenhouse gases, cooling, decreased atmospheric water vapor greenhouse weakens, more cooling. It's still a positive feedback, but it's working in the opposite direction. Okay, here's their result, and this is complicated, too many curves, but we only have to really focus on one. What they did was they took a big fancy computer model of climate, and they just arbitrarily zeroed out the CO2 and the methane and the other greenhouse gases, except for water vapor, and started the model up from a realistic state like the present climate, and ran it forward for a period of 50 years or so. And look at the, first look at the temperature. The temperature falls like a rock and gradually levels out at about minus 20 something, and it started out at plus 12 or 13. So tremendous cooling. Remember, these are degrees C. Why did that happen? Look what happens to the water vapor. It goes down to about 1/10 of what it was in the present climate. So take out the CO2 and the water vapor feedback will turn the planet into an ice bowl. And it does so in a time scale of about 20 years. The sea ice cover goes up to like 50% over the Earth. Okay, so take away the CO2 and what happens? The water vapor feedback leads to a dramatic cooling, and the sea ice feedback, of course, helps. So I'm done. This is my last slide. Take-home messages. First of all, the climate system does what it takes to balance the Earth's energy budget. That's basically where the climate comes from. The Earth's surface is heated by the sun, as we all know, but as we don't all know, it's heated twice as much by downward infrared from the atmosphere. This is not a subtle thing. Thunderstorms, the Hadley cells, and mid-latitude storms carry the energy both upward, so it can get out to space, and poleward, so it warms up the polar regions and cools the tropics. Infrared carries the energy the rest of the way out to space. The essence of climate change, the basic idea in rough numbers, can be got on the back of an envelope. The role of computer models is to add important details. And finally, water vapor feedback is a very strong factor in determining the strength of climate change in response to something like increasing CO2. Thank you.